Tonight, we're going to take a journey across something that sounds impossible. We're going to cross our entire galaxy from one edge to the other and calculate exactly how long it would take. Because here's what most people don't realize. The Milky Way is so staggeringly vast that even traveling at speeds that seem impossibly fast, crossing it would take longer than you can imagine. And by the end of tonight, you're going to understand just how isolated we truly are in this massive cosmic structure we call home. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the fundamental question. How long would it take to cross the Milky Way, to travel from one edge of our galaxy to the opposite side? The Milky Way is about 100,000 light-years across. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second, or about 300,000 kilometers per second. In 1 year, light covers about 5.88 trillion miles, or about 9.46 trillion kilometers. So when we say the Milky Way is 100,000 light-years across, we're saying it's about 588 quintillion miles from edge to edge, or about 946 quintillion kilometers. That's the distance we're talking about crossing. The first thing to understand is that conventional speeds are utterly inadequate. The fastest human-made object is currently the Parker Solar Probe, a NASA spacecraft studying the Sun. At its peak velocity, it reached about 430,000 miles per hour, or about 692,000 kilometers per hour. That's incredibly fast, about 1/600th the speed of light. Fast enough to circle Earth's equator in less than 6 minutes. It's the fastest thing humanity has ever built. And yet, at that speed, crossing the Milky Way would take over 150 billion trillion years. That's more than 11 trillion times the age of the universe. Chemical rockets, ion drives, nuclear propulsion, even gravity assists. All of these are far too slow. The distances in the galaxy dwarf anything achievable with conventional spacecraft. We need to think in terms of light speed itself. Light is the fastest thing in the universe. Nothing with mass can travel at light speed. But for this thought experiment, let's imagine we could. At exactly the speed of light, crossing the Milky Way takes 100,000 years by definition. 100 millennia. That's the time span from when modern humans first began leaving Africa and spreading across the globe to now. If you left one edge of the Milky Way at light speed, when anatomically modern humans first appeared on Earth, you'd be arriving at the other edge right about now. Even the fastest thing in the universe needs 100 millennia to make the journey. But here's where relativity changes everything. According to Einstein's special theory of relativity, time slows down as you approach the speed of light. From the perspective of someone traveling at light speed, the journey would be instantaneous. No time would pass at all. But from the perspective of someone watching from outside, someone stationary relative to the galaxy, the trip still takes 100,000 years. This is the strange nature of relativity. Time is not absolute. It depends on how fast you're moving. Of course, nothing with mass can actually reach light speed. The closer you get, the more energy it takes to accelerate further, and you'd need infinite energy to actually reach it. So let's be more realistic. At 99% the speed of light, the journey takes about 101,000 years from an outside perspective. But time dilation kicks in. For the traveler, only about 14,000 years pass. still far longer than human civilization has existed. Pushed to 99.9% light speed, and the traveler experiences roughly 4,500 years, while 100,000 years pass outside. At 99.99%, it's about 1,400 years of ship time. And if you could reach 99.99999% the speed of light, 7 nines after the decimal, time dilation becomes extreme. The journey takes 100,000 years from the outside, but only about 1.4 years for the traveler. Less than 17 months. Suddenly, crossing the Milky Way doesn't sound impossible. From the traveler's perspective, it's a long trip, but it's within a human lifetime, comparable to a long ocean voyage in the age of exploration. This is the key insight. Near light-speed travel, combined with time dilation, makes galactic crossing theoretically survivable. Not easy, not anywhere close to our current capabilities, but possible in principle. Of course, there are enormous practical problems with this. First, we have no way to accelerate anything to 99.9999% the speed of light. The energy requirements are staggering. To accelerate even a small spacecraft to that speed would require more energy than humanity has produced in its entire history. Second, even if you could somehow accelerate to that speed, traveling through interstellar space at such velocities would be incredibly dangerous. Space is not empty. There are atoms of hydrogen floating around, tiny dust grains, small rocks. At normal speeds, these pose no threat. But at 99.9999% light speed, even a single hydrogen atom hits with enormous energy. A dust grain would impact like a nuclear bomb. You'd need shielding so advanced it's beyond our current understanding of materials science. Third, even if you survived the journey, you'd face a serious problem when you arrived. 100,000 years would have passed on Earth. Everyone you knew would be gone. Civilizations would have risen and fallen. Humanity itself might have changed beyond recognition, or might not exist at all. You'd be traveling into the far future with no way back. These are not small obstacles. They're fundamental challenges that might never be overcome. But the point of this exercise is not to plan an actual journey across the Milky Way. It's to understand the scale involved and what physics tells us about the possibility. At everyday human speeds, crossing the Milky Way is essentially impossible. The time required is longer than the universe has existed. Even at light speed, the journey takes 100,000 years from an outside perspective, though time dilation makes it potentially survivable from the traveler's viewpoint if you could get close enough to light speed. The Milky Way is simply vast beyond human comprehension. Now, there's another wrinkle we haven't discussed yet: the route. We've been assuming you travel in a straight line from one edge to the other, but that's not necessarily the most interesting path. What if you wanted to cross the Milky Way by traveling through the center? The center of the Milky Way is about 26,000 light-years from Earth. We're about halfway out from the center to the edge. If you traveled from our position straight through the galactic center to the opposite edge, you'd cover about 100,000 light-years total. But traveling through the center presents special challenges. The center of the Milky Way is densely packed with stars. Near the very center, there's a supermassive black hole called Sagittarius A. It has a mass of about 4 million times the mass of the Sun. Getting too close to that black hole would be dangerous. Its gravity would tear anything apart. There's also intense radiation near the galactic center. X-rays and gamma rays from the accretion disk around the black hole and from other high-energy processes. Any traveler would need serious shielding to survive passing through that region. So, maybe going through the center isn't the best route. What about going around? The Milky Way is a spiral galaxy. It has a disc-like structure with spiral arms radiating out from the center. If you stayed within the disk and followed the spiral arms, you'd travel a longer path, but you'd avoid the most dangerous regions. Of course, a longer path means more time, even at high speed, but you might increase your chances of survival. The Milky Way isn't a uniform structure. It has denser regions and emptier regions. The spiral arms contain more stars, more gas, more dust. The spaces between the spiral arms are quieter, less crowded. A smart traveler would chart a course through the less dense regions to minimize the risk of collisions with interstellar matter. But even with the best route, even avoiding the center and the densest star-forming regions, you're still crossing 100,000 light-years. The journey still takes at minimum 100,000 years from an outside perspective and requires speeds very close to light speed to be survivable from the traveler's perspective. There's no way around the fundamental constraint imposed by the size of the galaxy and the speed of light. Here's another question worth considering. What would you see along the way? Imagine you're in a spacecraft traveling at 99.9999% the speed of light, making the crossing in about 17 months of ship time. What would the journey look like? First, everything would be severely distorted by relativistic effect. Light from objects ahead of you would be blue shifted, compressed into higher energy radiation. Light from objects behind you would be red shifted, stretched into lower energy radiation. The stars ahead would appear brighter and bluer. The stars behind would appear dimmer and redder. There's also an effect called relativistic beaming. Light that would normally be spread evenly in all directions gets concentrated into a beam pointing in your direction of travel. So most of the light you see would be coming from directly ahead. Your view would be like looking down a tunnel. Everything in your peripheral vision would be compressed into a narrow cone in front of you. The stars themselves would streak past. At that speed, you'd pass a star every few seconds of ship time, though from the outside perspective, you'd be taking years to travel between neighboring stars. You'd see the structure of the galaxy unfolding. The spiral arms, the denser regions packed with young blue stars, the quieter regions between the arms, the thin disk of the galaxy giving way to the thicker halo of old stars surrounding it. And you'd see the center approaching. The bright glow of millions of stars crowded together, the intense radiation from Sagittarius A, though hopefully from a safe distance if you routed around it. Then as you passed the center and headed toward the far edge, you'd see the structure again, but from the opposite perspective, the spiral arms from the other side, the far edge of the disk approaching. It would be the most spectacular voyage imaginable, a front-row seat to the structure and beauty of our entire galaxy. But it would also be lonely, unimaginably lonely, because while you experienced 17 months, 100,000 years would pass back home. Everything and everyone you knew would be gone. That's the cruel paradox of near-light speed travel. It makes the journey survivable for the traveler, but it cuts them off completely from their origin. Let's talk about energy for a moment, because the energy required to accelerate to near-light speed is truly staggering. To accelerate a 1-ton spacecraft to 99.99999%, the speed of light requires about 90 quintillion joules of kinetic energy. That's 90 billion joules. To put that in perspective, the world's total energy consumption in a year is about 600 quintillion joules. So accelerating a single 1-ton spacecraft to that speed would require about 15% of humanity's entire annual energy consumption, and that's just the kinetic energy. That doesn't account for inefficiencies in the propulsion system, which would likely be substantial. A realistic estimate might require several times that much total energy input, and 1 ton is tiny for a spacecraft. A spacecraft capable of carrying people, life support systems, radiation shielding, and supplies for a journey lasting months would mass much more than 1 ton. The International Space Station masses about 420 tons. A deep space vessel would need to be somewhere in that range or larger. If we scale up to a 420-ton spacecraft, the energy requirement scales proportionally. We'd need about 600 sextillion joules. That's about 100 times humanity's total annual energy consumption. Where would that energy come from? Chemical rockets won't work. The amount of fuel required would itself mass far more than the spacecraft, and you'd need fuel to accelerate that fuel, creating a vicious cycle. Nuclear fission or fusion might work in principle. Matter, antimatter annihilation, is the most energy-dense process known, converting mass directly to energy. According to Einstein's equation, E equals mc squared. If you had a kilogram of matter and a kilogram of antimatter and annihilated them completely, you'd get about 180 quadrillion joules. To accelerate a 420-ton spacecraft to 99.9999% light speed, you'd need to annihilate about 3,300 kilograms of matter with an equal amount of antimatter. That's about 6.6 tons total of matter-antimatter fuel. That's a lot, but it's at least conceivable. The problem is, we have no way to produce or store antimatter in anything close to those quantities. The total amount of antimatter ever produced by humanity is measured in nanograms, a few billionths of a gram. We'd need to increase production by a factor of trillions. We'd also need a way to store it safely, because antimatter annihilates instantly upon contact with normal matter. These are not small engineering challenges. They might be insurmountable. But let's assume, for the sake of argument, that some future civilization solves these problems. They figure out how to produce and store antimatter in large quantities. They build a spacecraft with advanced propulsion, radiation shielding, and life support. They send a crew on a journey across the Milky Way at 99.99999% the speed of light. The crew experiences about 17 months of travel time. They see the entire galaxy unfold before them. They cross 100,000 light years. They arrive at the far edge. What then? 100,000 years have passed on Earth. The civilization that sent them is long gone. Any message they send back will take 100,000 years to arrive. They're effectively cut off from their origin. They're on their own. This is the reality of galactic scale travel. Even at nearly the speed of light, even with time dilation working in your favor, the practical isolation is complete. You can cross the galaxy in a human-relevant time frame from your own perspective. But you can never really go home. Now, let's consider a different kind of journey. What if instead of crossing the Milky Way from edge to edge, we wanted to explore it? Visit multiple star systems. Stop and investigate planets. Search for life. This changes everything. Because now, we're not just covering distance. We're spending time at each destination. Let's say we want to visit 1,000 star systems spread across the Milky Way. We'll pick them to give a representative sample of the galaxy's structure. Some in the spiral arms, some between the arms, some near the center, some in the halo. The average distance between stars in our neighborhood is about 5 light-years. But star density varies. Near the center, stars are much more densely packed, maybe as close as 1/10 of a light-year apart. In the halo and in the spaces between spiral arms, stars are more spread out, maybe 10 or even 20 light-years apart. Let's assume an average travel distance of 5 light-years between each stop. Visiting 1,000 systems means traveling about 5,000 light-years total. At 99.99999% light speed, that's about 5,000 years of outside time, but only about 2.4 months of ship time for the travelers. 2.4 months of travel time, total. Sounds manageable. But then, we have to add the time spent at each star system. If we spend just 1 week at each system, studying the star, investigating any planets, searching for signs of life or interesting phenomena, that's 1,000 weeks total. 1,000 weeks is about 19 years. So the journey would take 2.4 months of travel time plus 19 years of exploration time, for a total of about 19.2 years of ship time. That's a long time, but it's within a human lifetime. A crew could conceivably complete such a mission. But here's the problem. From the outside perspective, the time elapsed is different. The travel time is 5,000 years. The exploration time, since they're essentially stationary while exploring each system, is the same 19 years. Total outside time is about 5,019 years. 5 millennia pass back home while the crew experiences 19 years. They leave in the year 2025. They return in the year 7044. Every civilization, every language, every culture they knew is gone. Humanity itself might have changed beyond recognition. This is the fundamental problem with exploring the galaxy. Time dilation helps the travelers, but it doesn't help anyone back home who's waiting for results or hoping to see the explorers return. Could we solve this by going slower? If we traveled at a more modest speed, say 10% the speed of light, time dilation would be minimal. The crew and the people back home would age at nearly the same rate. But now, the travel time explodes. 5,000 light-years at 10% light speed is 50,000 years of travel time. Add 19 years of exploration, and you get 50,019 years total. That's longer than all of recorded human history. No crew could survive that long. You'd need a generation ship, a spacecraft where multiple generations are born, live, and die during the journey. The original crew would be long gone before the mission even reached the first destination. Their great-great-great-great-grandchildren might explore the first few star systems. Their descendants, hundreds of generations later, might complete the mission. This is the trade-off. Fast travel means survivable ship time, but extreme time dilation and isolation from home. Slow travel means staying connected to home time, but the journey takes longer than human lifespans, or even civilizations can endure. There's no good solution. The Milky Way is simply too large for the kind of exploration we might dream about. Here's an interesting thought. What about using not a spacecraft, but a signal? Instead of sending people, or even probes, what if we just sent information? A radio signal or a laser beam carrying a message? How long would it take a signal to cross the Milky Way? Signals travel at the speed of light. So a signal sent from one edge of the Milky Way takes 100,000 years to reach the other edge. If we sent a signal from Earth toward the far edge of the galaxy, It would arrive 100,000 years from now. If someone on the other side received it and immediately sent a reply, that reply would take another 100,000 years to get back to us. Total round-trip time, 200,000 years. That's twice as long as modern humans have existed. This has profound implications for any attempt to communicate across the galaxy. Even if there are other intelligent civilizations in the Milky Way, even if they're trying to communicate, the time lag makes conversation impossible. You could send a message, but you'd be gone long before any reply arrived. Your civilization might be gone. Your species might be extinct. This is why SETI, the search for extraterrestrial intelligence, looks for any signal at all, rather than hoping for two-way communication. If we detect a signal from another civilization, it's essentially a message in a bottle. It was sent thousands or tens of thousands of years ago. It's not a conversation. It's archaeology. We'd be learning about a civilization as it existed in the distant past, with no way to know if it still exists now. And if we wanted to respond, our message wouldn't arrive until thousands of years in their future. The scale of the galaxy makes real-time communication impossible. Even one-way communication is challenging because the timescales involved are so long. This isolation is baked into the structure of the universe. The speed of light is finite. Distances in the galaxy are enormous. These two facts combine to create a fundamental barrier. We can know about distant parts of the galaxy, but only their past, never their present. We can send signals, but we'll never hear the reply. This is the reality of living in a galaxy 100,000 light-years across. Now, let's think about this from a different angle. Instead of how long it takes to cross the Milky Way, let's ask how much of the Milky Way we could explore in a given amount of time. Suppose we have a spacecraft that can travel at 50% the speed of light. That's fast, but not so close to light speed that extreme time dilation kicks in. At 50% light speed, time dilation is only a factor of about 1.15. So the crew's experience of time is roughly similar to the passage of time back home. In one human lifetime, say 80 years, how much of the Milky Way could that spacecraft explore? Traveling at 50% light speed, the spacecraft can cover about 40 light-years in 80 years of time. 40 light-years is a tiny fraction of the Milky Way's 100,000 light-year diameter. It's 4/100,000ths of the distance across the galaxy, 0.04%. In an entire human lifetime of continuous travel, a spacecraft moving at half the speed of light could cross less than 1/20th of 1% of the galaxy's diameter. Put another way, it would take about 2,500 lifetimes to cross the galaxy at that speed, or about 200,000 years, 200 millennia. Modern humans have existed for about 300,000 years. So crossing the Milky Way at 50% light speed would take most of the time that our species has existed. What if we devoted not one lifetime, but the entire history of human civilization to the journey? Recorded history goes back about 5,000 years. At 50% light speed, in 5,000 years, you could cover about 2,500 light-years. That's about 2.5% of the galaxy's diameter. Still, a tiny fraction. You'd need 40 trips of 5,000 years each to cross the entire galaxy. That's 200,000 years again. No matter how we calculate it, the answer keeps coming back to the same basic conclusion. Crossing the Milky Way takes time measured in many thousands or hundreds of thousands of years, unless you travel very close to the speed of light and accept the resulting time dilation. There's no shortcut. The galaxy is vast, and the speed of light is finite. Those two facts combine to make galactic scale travel incredibly difficult. Could there be a loophole? What about wormholes, or warp drives, or other science fiction concepts? These ideas come from general relativity, Einstein's theory of gravity. General relativity describes gravity as the curvature of space-time. Massive objects like stars and black holes curve space-time around them, and other objects follow the curves. In principle, if you could manipulate space-time in certain ways, you might be able to create shortcuts. A wormhole is a hypothetical tunnel through space-time connecting two distant points. If a wormhole connected one edge of the Milky Way to the other, you could cross the galaxy almost instantaneously by traveling through the wormhole instead of across normal space. The problem is we have no idea how to create a wormhole. The physics suggests that even if wormholes can exist, they'd require exotic matter with negative mass or negative energy density to hold them open. We've never observed anything with negative mass. It might not exist. Even if it does exist, we don't know how to produce it or manipulate it. Wormholes remain firmly in the realm of speculation. Warp drives are another idea from general relativity. The concept is that instead of moving through space, you manipulate space itself. You contract space in front of your spacecraft and expand space behind it, creating a bubble that carries you along faster than light relative to the surrounding space. This doesn't violate relativity because you're not moving faster than light through space. You're moving space itself. The problem, again, is exotic matter. The calculations suggest that creating a warp bubble would require enormous amounts of negative energy density. More than likely exists in the entire visible universe. Even optimized versions of the warp drive, proposed by physicists like Miguel Alcubierre, still require exotic matter and enormous energies. There's no known way to build one. So, while wormholes and warp drives are fun to think about and make great science fiction, they're not practical solutions to crossing the Milky Way. At least not with our current understanding of physics. Maybe some future breakthrough will change that. Maybe there's something fundamental about space-time that we don't understand yet. But based on what we know now, we're stuck with the speed of light as a fundamental limit. And at the speed of light, crossing the Milky Way takes 100,000 years. Let's zoom out even further. We've been talking about crossing the Milky Way, but what about crossing the local group? The local group is the collection of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies. It spans about 10 million light-years. At light speed, it would take 10 million years to cross the local group. 10 million years is longer than the entire history of the human lineage. Our species, Homo sapiens, has existed for about 300,000 years. Our genus, Homo, has existed for about 2.5 million years. The entire human evolutionary line, going back to our split from other apes, is only about 6 or 7 million years. Crossing the local group would take longer than humans have existed as a distinct lineage. What about crossing the Virgo supercluster? That's the larger structure that contains the local group and many other galaxy groups and clusters. It spans about 110 million light-years. At light speed, 110 million years. The dinosaurs went extinct 66 million years ago. They ruled the Earth for about 170 million years before that. Crossing the Virgo supercluster would take about as long as the entire age of the dinosaurs. And what about crossing the observable universe? The observable universe is about 93 billion light-years across. But it's not as simple as saying it takes 93 billion years to cross at light speed because the universe is expanding. While you're traveling, space itself is stretching. The destination is moving away from you. Depending on the expansion rate, it might be impossible to ever reach the far edge of the observable universe, even at light speed. The expansion of space could carry it away faster than you're approaching. This is the ultimate limit. Not just the speed of light, but the expansion of the universe itself. Some parts of the universe are receding from us faster than light because space itself is expanding. We can never reach them, no matter how fast we travel. They're beyond our cosmic horizon, permanently inaccessible. So, when we ask how long it takes to cross the Milky Way, we're actually asking a relatively modest question. The Milky Way is our local neighborhood, 100,000 light-years across. Vast beyond human comprehension, but tiny compared to the larger structures of the universe. And even crossing this relatively small structure, even crossing our own galactic home, requires either 100,000 years at light speed or near light speed. Travel with all its attendant challenges and time dilation effects. The Milky Way is immense, and we are very, very small. Let me give you one more perspective on this, one that brings it back to human terms. Imagine you're standing on Earth, looking up at the night sky. You see the Milky Way stretching across the darkness, a band of light made of billions of distant stars. Every one of those stars is unreachably far away in human terms. The nearest star, Proxima Centauri, is about 4.24 light-years away. At current spacecraft speeds, reaching it would take tens of thousands of years. At light speed, 4.24 years. That's the nearest star. The far edge of the Milky Way is about 100,000 light-years away, or about 23,600 times more distant than Proxima Centauri. If Proxima Centauri represents the edge of what we might someday reach with a very long spacecraft mission, the far edge of the galaxy represents something vastly more distant. It's not just farther. It's in a completely different category of distance. Within our own galaxy, within the structure we call home, there are regions so distant that they might as well be in another universe for all the possibility we have of reaching them. And yet, it's all one connected structure. The Milky Way is a single galaxy. All its stars are gravitationally bound together, orbiting a common center. We're part of that structure. Every star you see is part of the same cosmic family. But it's a family spread across such vast distances that we'll never meet most of our relatives. This is the paradox of the Milky Way. It's home, but most of it is forever beyond our reach. We can observe it. We can study it with telescopes. We can understand its structure, its composition, its evolution, but we can't explore it directly, not with any technology we have or are likely to have in the foreseeable future. The distances are simply too great. The time scales are simply too long. We're confined to our tiny corner of the galaxy, able to look out and wonder, but unable to travel and see for ourselves. There's something both humbling and beautiful about that. We live in a galaxy so vast that light takes 100,000 years to cross it. A galaxy containing somewhere between 100 billion and 400 billion stars. A galaxy that's been our home for as long as Earth has existed, for as long as life has existed, for as long as humans have looked up at the night sky and wondered about those points of light. We're here, in this one specific place, orbiting this one specific star, in this one specific spiral arm, and the rest of the galaxy, the vast majority of it, remains out there, distant. mysterious, beautiful, forever beyond our physical reach, but close enough that we can see it, study it, and understand our place within it. This is what it means to ask how long it would take to cross the Milky Way. It's not just a question about speed and distance. It's a question about what's possible and what's not, about the limits imposed by physics and the scale of the universe, about our place in a cosmos so large that even our home galaxy dwarfs us. We've calculated the numbers: walking 200 quadrillion years, driving over a quadrillion years, fastest spacecraft ever built, about 150 billion trillion years, light speed 100,000 years, near light speed with extreme time dilation, potentially as little as a year or two of ship time, but at the cost of 100,000 years passing everywhere else. These numbers tell us something fundamental. Crossing the Milky Way is possible in principle. Physics doesn't forbid it, but practically it's beyond us, beyond our technology, beyond our lifespans, beyond our civilization's time span. Unless something dramatic changes, unless we discover new physics or develop technologies we can't currently imagine, we're staying in our corner of the galaxy. And maybe that's okay. Maybe it's enough to know that the Milky Way is out there, to study it from a distance, to understand its structure and history, to wonder about the other worlds it contains, the other stars, the possible other civilizations. Maybe the journey across the galaxy isn't meant to be a physical one. Maybe it's an intellectual one, a journey of understanding rather than exploration. We've mapped the galaxy. We know its size, its shape, its composition. We know how stars form and die within it. We know about its central black hole, its spiral arms, its halo of old stars. We've measured distances across it using parallax, standard candles, redshift. We've detected planets around other stars and found that planetary systems are common. We've listened for signals from other intelligent civilizations. We've sent our own messages out into the galaxy, knowing they'll take tens of thousands of years to reach any possible recipients. In a sense, we've already crossed the galaxy, not physically, but in understanding. Our knowledge spans from one edge to the other. Our telescopes peer into its most distant corners. Our theories explain its birth, its evolution, its ultimate fate. Maybe that's the real answer to the question. How long does it take to cross the Milky Way? Physically, 100,000 years at light speed. Intellectually, we've already done it. The galaxy is vast, but human curiosity is vaster. We've reached across those 100,000 light years, with our minds, with our instruments, with our mathematics. We've crossed the Milky Way in the only way that really matters, by understanding it, by making it part of our story, by recognizing that we're not separate from it. We're within it, of it, made from its matter, powered by its stars, shaped by its history. The Milky Way is not something we cross. It's something we live in, something we're part of. And that's more profound than any journey could ever be. When you look up tonight at that band of stars stretching across the sky, remember that you're looking at home, not a destination, not a place to travel to, but home. The vast structure that contains us, shapes us, defines the cosmic context in which we exist. 100,000 light years across, hundreds of billions of stars, trillions of worlds. And somewhere in there, orbiting one ordinary yellow star, a small rocky planet where life arose, where consciousness emerged, where beings evolved who could look up, measure the distances, calculate the time it would take to cross that vast expanse, and understand their place in it all. That's us. That's our story. Not travelers crossing the galaxy, but part of the galaxy itself, made from it, shaped by it, forever connected to it, even if we never physically traverse it. The Milky Way is vast beyond comprehension. Crossing it would take 100,000 years at the speed of light, much longer at any realistic speed. Potentially survivable with near light speed travel and time dilation, but at the cost of becoming disconnected from everything you knew. These are the facts. The physics is clear. The distances are measured. The timescales are calculated. But there's more to this story, much more. Because understanding how long it takes to cross the Milky Way opens up deeper questions about what the galaxy actually is, how it formed, and what crossing it would really mean. Let's step back and think about the Milky Way not just as a distance to cross, but as a structure with history, with dynamics, with a future. The Milky Way didn't always exist in its current form. About 13.6 billion years ago, shortly after the Big Bang, the first stars began forming. These were massive stars, made almost entirely of hydrogen and helium, the only elements that existed in abundance back then. They lived fast and died young, exploding as supernovas and scattering heavier elements into space. Those heavier elements, carbon, oxygen, iron, and all the rest, became the building blocks for the next generation of stars, and for planets, and eventually for life. The Milky Way formed from the gradual accumulation of gas, stars, and dark matter over billions of years. Small galaxies merged together. Gas clouds collapsed under their own gravity. Stars formed in clusters and then spread out as those clusters dissolved. The whole process took billions of years. Even today, the Milky Way is still growing. It's still absorbing smaller galaxies that wander too close. The Sagittarius dwarf elliptical galaxy is currently being torn apart and absorbed by the Milky Way's gravity. Its stars are being stripped away and added to our galaxy. In a few billion years, there won't be a separate Sagittarius dwarf. It'll be fully integrated into the Milky Way. This is how galaxies grow, through mergers and accretion. The Milky Way we see today is the result of countless mergers over billions of years. Many of the stars in our galaxy's halo, the spherical region surrounding the disk, probably came from smaller galaxies that merged with ours long ago. When you think about crossing the Milky Way, you're thinking about crossing a structure with billions of years of history. Every star you'd pass has its own story. Some are ancient, nearly as old as the universe itself, formed in the very early days of the galaxy. Others are young, only a few million years old, still surrounded by the gas and dust from which they formed. Some are solitary, like our Sun. Others are in binary or multiple star systems, locked in gravitational dances with companion stars. Some are in the prime of their lives, fusing hydrogen into helium in their cores. Others are dying, swelling into red giants, or collapsing into white dwarfs, neutron stars, or black holes. The diversity is staggering, and you'd see all of it on a journey across the galaxy. Different types of stars in different stages of life. Different environments, from the crowded stellar nurseries in spiral arms to the quiet spaces between. Let's talk about those spiral arms for a moment, because they're one of the most striking features of the Milky Way, and crossing the galaxy means crossing through them multiple times. The Milky Way has several major spiral arms. The Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and others. These arms aren't fixed structures, like the arms of a pinwheel. They're density waves, regions where stars, gas, and dust are more concentrated. As the galaxy rotates, the spiral pattern remains, even though individual stars move in and out of the arms. Think of it like a traffic jam on a highway. The jam itself stays in roughly the same place, even though individual cars are constantly entering and leaving it. Spiral arms work the same way. They're regions of higher density that persist even as stars orbit through them. Inside the spiral arms, the density of gas is higher. That means star formation is more active. You see lots of young, hot blue stars in spiral arms. These massive stars live fast and die young, only a few million years typically. They don't have time to drift far from where they formed before they explode as supernovas. So spiral arms are marked by bright blue regions of active star formation. Between the spiral arms, star formation is less active. You find older stars, cooler and redder. The environment is quieter. Our Sun is currently between major spiral arms in the Orion Spur. It's a relatively safe place, not too crowded. Supernova explosions are rare enough that life on Earth has had billions of years to evolve without being sterilized by nearby blasts of radiation. If we were in a dense spiral arm, supernovas would be more common. The radiation from nearby explosions could strip away Earth's atmosphere or damage the ozone layer. Life might never have had the chance to develop. So, our position in the galaxy, between major spiral arms, has been important for our existence. On a journey across the Milky Way, you'd cross through spiral arms and through the spaces between them. You'd see the environments change. Dense regions filled with glowing gas and young stars. Quieter regions with older, more sedate, stellar populations. The variation would be spectacular. Now, let's think about what else you'd encounter on a journey across the galaxy. Stars are just part of the story. There are also nebulae, vast clouds of gas and dust. Some nebulae are stellar nurseries, regions where new stars are forming. The Orion Nebula is a famous example, visible to the naked eye as a fuzzy patch in Orion's sword. It's about 1,350 light-years away, relatively close by galactic standards. Inside the Orion Nebula, hundreds of stars are forming right now. The gas is collapsing under gravity, fragmenting into dense cores that will become stars. In a few million years, those young stars will blow away the remaining gas with their stellar winds and radiation, leaving behind a new star cluster. Other nebulae are the remains of dead stars. Planetary nebulae form when a star like the Sun reaches the end of its life, swells into a red giant, and then sheds its outer layers into space. The hot core of the star, now a white dwarf, illuminates the expanding shell of gas, creating beautiful glowing structures. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, all are planetary nebulae. Each one represents a star that died and returned its material to the interstellar medium. Supernova remnants are even more dramatic. When a massive star explodes, it blasts its outer layers into space at tremendous speeds. The expanding shell of debris, enriched with heavy elements forged in the explosion, crashes into surrounding gas and creates a glowing nebula. The Crab Nebula is a famous supernova remnant. The star that created it exploded in the year 1054. Chinese and Arab astronomers recorded seeing a bright new star in the sky, visible even during the day for weeks. Nearly 1,000 years later, we can see the expanding debris cloud, still glowing from the energy of that explosion. Crossing the Milky Way, you'd see countless nebulae, some so faint you'd need instruments to detect them. Others bright and spectacular, spanning tens of light years across. Each one a reminder that the galaxy is not static. It's constantly recycling material. Stars form from gas clouds. They live and die. They return their material to space. That material mixes with other gas and eventually forms new stars. The cycle continues. The atoms in your body were once inside stars that lived and died billions of years ago. Those stars formed from gas that came from even earlier stars. It's a chain, stretching back to the beginning of the galaxy. On a journey across the Milky Way, you'd be traveling through that history, seeing the cycle in action everywhere you looked. You'd also encounter star clusters. These are groups of stars born together from the same gas cloud. Open clusters are loose groups of dozens or hundreds of stars, found mainly in the galactic disk. The Pleiades is a well-known open cluster, visible as a tight group of blue stars in the constellation Taurus. It's about 445 light-years away and contains several hundred stars, though only the brightest are visible to the naked eye. The stars in the Pleiades are young, only about 100 million years old. Eventually, over hundreds of millions of years, the cluster will disperse as the stars drift apart. But for now, they're still together, moving through the galaxy as a group. Globular clusters are much larger and older. These are spherical collections of hundreds of thousands or even millions of stars, densely packed together. They orbit in the halo of the galaxy, above and below the disk. Globular clusters are ancient, typically 10 billion to 13 billion years old, nearly as old as the galaxy itself. The stars in them are old and metal-poor, meaning they contain very little of the heavy elements found in younger stars. That's because they formed early, before the galaxy had been enriched with much material from supernova explosions. Crossing the Milky Way from the disk out into the halo, you'd pass through regions populated by globular clusters. Seeing them would be extraordinary. Imagine approaching a cluster containing 1 million stars packed into a sphere only 100 light-years across. The density of stars near the center would be incredible. If you were on a planet orbiting a star in the core of a globular cluster, your night sky would be filled with thousands of bright stars. There would be no darkness. The combined light of all those stars would make your night sky brighter than twilight on Earth. It would be beautiful, but it would also be hazardous. The close proximity of so many stars would mean more frequent gravitational interactions. Planets could be stripped from their orbits. Stars could pass close enough to disturb the inner structure of planetary systems. Life might struggle to survive in such a chaotic environment, but that's speculation. We don't know if planets even form in globular clusters. The stars are so metal-poor that there might not have been enough rocky material to form planets in the first place. It's one of the many mysteries about these ancient stellar cities. Let's talk about another feature you'd encounter: the galactic center. The center of the Milky Way is about 26,000 light-years from Earth. We can't see it directly in visible light because there's too much dust in the way, blocking our view. But in infrared and radio wavelengths, which can penetrate the dust, we can observe what's happening there. The galactic center is a crowded, chaotic place. Stars are packed much more densely than in our neighborhood. There are millions of stars within a few light-years of the exact center. And at the very center, there's Sagittarius A, the supermassive black hole we mentioned earlier. Sagittarius A has a mass of about 4.1 million times the mass of the Sun. It's relatively quiet right now, not actively feeding on much material, but it's still a powerful gravitational anchor holding the inner galaxy together. Around Sagittarius A, stars orbit at incredible speeds. The star S2, for example, completes an orbit around the black hole in about 16 years. Its orbit is highly elliptical, bringing it as close as about 17 light hours from the black hole at its nearest approach. At that distance, it's moving at about 3% the speed of light. Observing S2 and other stars near Sagittarius A has been crucial for confirming that the black hole exists. You can't see the black hole directly. It emits no light, but you can see stars orbiting something massive and invisible. The only explanation that fits is a supermassive black hole. On a journey across the Milky Way, passing near the galactic center would be one of the highlights. Assuming you routed carefully to avoid getting too close to Sagittarius A, you'd see an environment unlike anywhere else in the galaxy. A densely packed core of stars, intense radiation from hot gas orbiting the black hole, stars moving at relativistic speeds. It would be spectacular, but also dangerous. The radiation levels would be high enough to require serious shielding. The gravitational field near the black hole would be intense. Passing through that region would require careful navigation and robust spacecraft design. But the reward would be unmatched. A view of the heart of our galaxy, the gravitational center around which hundreds of billions of stars orbit. Another feature worth mentioning is the galactic halo. This is the roughly spherical region surrounding the disk of the Milky Way. It contains old stars, globular clusters, and most importantly, dark matter. The halo extends much farther than the visible disk. The disk is about 100,000 light-years across and about 1,000 light-years thick, but the dark matter halo extends out to perhaps 600,000 light-years or more. Most of the Milky Way's mass is in that halo, not in the visible disk. The stars we see, the gas, the dust, all of that is only about 10 to 15% of the total mass. The rest is dark matter. We don't know what dark matter is made of. We can't see it directly, but we can measure its gravitational effects. The outer stars in the galaxy orbit faster than they should, based on the visible matter alone. The only explanation is that there's a lot of additional mass out there, invisible mass, providing the extra gravity needed to explain the orbital speeds. That's dark matter. On a journey across the Milky Way, you'd be traveling through the dark matter halo the entire time, but you wouldn't notice it directly. Dark matter doesn't interact with light or ordinary matter except through gravity. It would be there, surrounding you, making up most of the mass of everything around you, but you wouldn't see it or feel it. It's one of the great mysteries of modern astrophysics. How can most of the universe's mass be invisible to us? What is dark matter made of? Physicists have been searching for dark matter particles for decades with increasingly sensitive detectors, but so far they've found nothing. Whatever dark matter is, it's elusive. Now, let's think about the journey from another perspective. Not how long it takes, but what it would mean. If you're crossing the Milky Way, you're leaving everything familiar behind. Every constellation you've ever seen is a view from one specific location, Earth's position in the galaxy. Move a few hundred light years, and the constellations change. Familiar patterns break apart. New patterns emerge. Travel thousands of light years, and the sky looks completely different. Stars that were prominent from Earth are faint or invisible. Stars that were faint are now bright. The sun itself, if you could still see it at all, would be just another dim star lost among millions of others. Every reference point would be gone. Crossing the galaxy would be a journey into the unknown in the most literal sense. You couldn't navigate by the stars because the stars would be different everywhere you went. You'd need instruments, precise measurements of your position relative to the galactic center or to known pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation. They pulse with incredible regularity, some completing hundreds of rotations per second, each pulse timed to within microseconds. Because they're so regular, pulsars can serve as cosmic lighthouses. By measuring the timing of pulses from multiple pulsars, you can triangulate your position in the galaxy. NASA has even developed technology for spacecraft navigation using pulsars. The system is called Sextant, Station Explorer for X-ray timing and navigation technology. It demonstrated that a spacecraft could determine its position in space by detecting pulses from X-ray pulsars. This technology might be essential for any future deep space or galactic exploration. Because once you're far from Earth, far from the Sun, you can't rely on familiar landmarks. You need something universal. Pulsars fit that role perfectly. They're scattered throughout the galaxy. They pulse with clockwork precision, and they can be detected from great distances. A spacecraft crossing the galaxy would likely rely heavily on pulsar navigation. But even with perfect navigation, the psychological challenges would be immense. Humans evolved to live in one specific environment, on a planet's surface, under a particular star, with a particular view of the sky. We're adapted to Earth, to its gravity, its day length, its seasonal cycles, its familiar patterns. Remove all of that and put someone in a spacecraft traveling through empty space for months or years, even with time dilation, reducing the ship time, and you're asking them to cope with an environment for which they're not prepared. There would be no day and night in the natural sense. The spacecraft would have to create artificial cycles. No gravity unless the ship rotates to create artificial gravity through centripetal force. No familiar sky outside the windows. Just the slowly changing patterns of unfamiliar stars. The isolation would be profound. No possibility of communicating with Earth in real time. Even radio signals would take years or decades or centuries to arrive, depending on your distance. You'd be cut off, truly alone. This is one reason why the idea of generation ships comes up in discussions of galactic exploration. A generation ship is a spacecraft designed to support a population for many generations. The original crew who launched the ship know they'll never reach the destination. Their children won't reach it either, nor their grandchildren. Maybe after 10 or 20 or 50 generations, their descendants will arrive. But for most people on the ship, it's not a journey, it's a life. They're born on the ship, they live their entire lives on the ship, they die on the ship. For them, the ship is not a vehicle, it's the world. This raises profound ethical questions. Is it right to commit future generations to this fate? People who never chose to be part of the journey, who will never see Earth, who will live and die in a confined artificial environment, all for a mission they didn't volunteer for. Some argue that it's no different from being born on Earth. Nobody chooses to be born. Nobody chooses their circumstances. We're all, in a sense, on a generation ship called Earth, traveling through space around the Sun, around the galaxy. Others argue that there's a fundamental difference. Earth is a living world with vast diversity. A generation ship is a confined artificial environment. The ethical dimensions are different. There's no easy answer. But if crossing the galaxy at sub-light speeds requires generation ships, then these are questions we'd have to grapple with. Let's return to the physics for a moment and talk about a concept we haven't fully explored yet: the relativity of simultaneity. This is another strange consequence of Einstein's special theory of relativity. It says that events that are simultaneous in one reference frame are not simultaneous in another reference frame, moving relative to the first. Here's what that means for crossing the galaxy. Suppose you leave Earth at near light speed, headed for the far edge of the Milky Way. From your perspective on the ship, time is dilated. Let's say you're traveling at a speed where the time dilation factor is 10,000. So while 100,000 years pass for the outside universe, only 10 years pass for you. You experience a 10-year journey. But here's the strange part. In your reference frame, the frame of the moving spacecraft, the concept of what's happening back on Earth right now is different from what someone on Earth would say is happening right now. Because of the relativity of simultaneity, when you're 1 year into your journey from your perspective, the date back on Earth is not just 10,000 years later. The relationship between your ship time and Earth time is not a simple multiplication. The entire concept of simultaneous events across large distances breaks down when you're moving at relativistic speeds. Different observers in different reference frames will disagree about what's happening when. This means that crossing the galaxy doesn't just separate you in space. It separates you in time in ways that are deeply non-intuitive. The idea that there's a universal now, a single present moment that's the same everywhere in the universe, is wrong. Relativity tells us that there's no universal now. Simultaneity is relative. Different observers can disagree about which events happened first, which happened later, and which happened at the same time. As long as the events are separated by space-like intervals, meaning they're far enough apart that light couldn't travel from one to the other in the time between them, there's no unique answer to which happened first. This is one of the most profound insights of relativity. Time is not absolute. It's woven together with space into a four-dimensional structure called space-time. And how you move through space-time determines how you experience time. On a journey across the galaxy at near light speed, your experience of time would be radically different from the experience of anyone left behind. Not just slower, but fundamentally different in how it relates to events elsewhere in the universe. This raises philosophical questions about identity and continuity. If you cross the galaxy and return, you'll come back to a future Earth. Everyone you knew will be gone. Thousands or even hundreds of thousands of years will have passed. Are you still the same person? In one sense, yes. You've aged only a few years from your own perspective. Your memories, your personality, your identity are continuous. But in another sense, you're a person out of time. Everyone and everything that defined your life is gone. You're a relic from the ancient past, preserved by the physics of high-speed travel. Some people might find that exciting, an opportunity to see the future. Others might find it terrifying, a form of exile from which there's no return. There's also the question of purpose. Why would anyone cross the galaxy? What would be the goal? Exploration is one obvious answer. The desire to see what's out there, to visit other star systems, to search for life, to understand the diversity of worlds and phenomena that exist. Humanity has always been driven by exploration. We've explored every continent on Earth. We've sent probes to every planet in the solar system. The urge to explore seems fundamental to who we are. Crossing the galaxy would be the ultimate expression of that urge. But there might be more practical reasons too. Perhaps we're searching for resources. Maybe Earth's resources are depleted, and we need to find new sources of materials or energy. Maybe we're fleeing some catastrophe. A dying sun, a plague, a war, something that makes Earth uninhabitable and forces us to search for a new home. Or maybe we're searching for knowledge. Perhaps there's something at the far edge of the galaxy that we need to understand. A phenomenon we've detected but can't study from a distance. An anomaly that requires direct investigation. Or maybe we're not alone in the galaxy, and we're traveling to make contact with another civilization. The motivations would shape the journey. An exploration mission might make multiple stops, visiting many star systems. A refugee mission might head straight for a specific destination, a known habitable world. A contact mission might be following a signal, trying to reach whoever sent it. Each would be a different kind of journey, with different challenges and different risks. But all would require crossing vast distances. All would require dealing with the fundamental constraints of light speed and time dilation. All would involve leaving the familiar behind and venturing into the unknown. Let's consider one more scenario. What if the journey across the galaxy wasn't undertaken by biological creatures at all? What if we sent machines instead? Robotic probes, artificial intelligence, self-replicating spacecraft. Machines don't experience time the way we do. They can be shut down and reactivated. They can wait centuries or millennia without boredom or psychological strain. They don't need life support, food, water, or air. They're ideal for long journeys. This is actually the most realistic scenario for exploring the galaxy. Not crewed missions, but automated probes. We've already done this on a small scale. Voyager 1 and Voyager 2 were launched in 1977. They visited Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune. Then they continued onward, leaving the solar system entirely. They're now in interstellar space, still sending back data about the environment between the stars. Eventually, their power sources will fail, and they'll go silent. But they'll continue drifting through space forever, or until they collide with something. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called AC+, 793888. It's not a close approach, but it's the closest it will come to another star in the foreseeable future. If an alien civilization exists there and has the technology to detect the probe, they might find it. Onboard Voyager 1 and Voyager 2 are golden records, phonograph records containing sounds and images from Earth. They include greetings in 55 languages, music from different cultures, sounds of nature, and diagrams showing Earth's location in the galaxy. The records were intended as messages to any extraterrestrial intelligence that might find the probes. The chances of that are incredibly small, but the gesture is profound. We sent a piece of our world out into the galaxy. Voyager represents the beginning of humanity's presence beyond the solar system. In the future, we might send more advanced probes, faster spacecraft with better instruments, perhaps even self-replicating probes that could explore multiple star systems, building copies of themselves at each destination and sending those copies onward. This is called the von Neumann probe concept, named after mathematician John von Neumann, who developed the theory of self-replicating machines. A single self-replicating probe could, in principle, explore the entire galaxy. It arrives at a star system, gathers resources, builds copies of itself, and sends them to other star systems. Those copies do the same. The probes spread exponentially. Even at modest speeds, a fraction of light speed, a single probe could spawn enough copies to visit every star system in the galaxy in a few million years. That's a long time, but it's short compared to the age of the galaxy. If another civilization developed this technology and launched von Neumann probes billions of years ago, the galaxy could be filled with their probes by now. This is part of the Fermi paradox. The question of why we haven't detected any signs of extraterrestrial intelligence. If intelligent life is common, and if any of it develops technology like self-replicating probes, we should see evidence of it everywhere. But we don't. The galaxy appears empty of advanced civilizations, at least in our corner of it. Either intelligent life is very rare, or it doesn't last long enough to colonize the galaxy, or it chooses not to, or we're looking in the wrong way. Nobody knows the answer. But the question is deeply connected to the challenge of crossing the galaxy. Because if crossing the galaxy is as difficult as it seems, maybe that explains why we haven't encountered anyone else. Maybe the distances are simply too great for most civilizations to overcome. Maybe every civilization reaches the point where it can contemplate galactic exploration, but concludes, as we might, that the costs outweigh the benefits. Or maybe we're alone. Maybe Earth is the only place in the entire galaxy where life developed to the point of intelligence and technology. That would make us precious beyond measure. And it would make the question of crossing the galaxy somewhat moot, because there'd be nobody out there to meet. But we don't know. And the only way to find out for certain would be to explore, to send probes or missions to other star systems, to search for evidence of life or intelligence. That brings us back to the original question. How long would it take to cross the galaxy? And now we can see that the question has many dimensions. It's not just about physics and mathematics. It's about purpose, about risk, about what we hope to find and what we're willing to give up to find it. Physically, the answer is clear. At light speed, 100,000 years. At near light speed, with extreme time dilation, potentially as little as a year or two of subjective time for the travelers. At realistic spacecraft speeds, hundreds of thousands or millions of years. These are the numbers. They're set by the structure of the universe, by the size of the Milky Way and the speed of light. But the deeper questions remain. Should we try to cross the galaxy? What would we gain? What would we lose? Is it worth the cost, the risk, the isolation? Or should we stay in our corner of the galaxy, explore nearby star systems, and accept that most of the galaxy will remain forever beyond our reach? These are questions each generation will have to answer for itself. Because technology changes, understanding deepens. What seems impossible today might become possible tomorrow, or it might not. The universe doesn't care about our ambitions. It operates according to physical laws that don't bend to accommodate our desires. But within those laws, there's room for possibility, room for exploration, for discovery, for reaching out into the cosmos and seeing what's there. The Milky Way is vast. Crossing it would take lifetimes, generations, perhaps eons. But the human spirit, the spark of curiosity that drives us to ask these questions, doesn't measure itself against the easy or the achievable. It measures itself against the edge of the possible. And crossing the galaxy, while perhaps the most daunting journey imaginable, is not impossible, just difficult. Incredibly, staggeringly difficult, but not impossible. And maybe that's enough. Maybe knowing that it could be done, even if we never do it, is valuable in itself. It reminds us that we live in a universe governed by comprehensible physical laws, that we can calculate what's required to cross 100,000 light years, that we can imagine journeys that dwarf anything in human history, that we're part of something immense, something that extends far beyond our tiny planet and our brief lives. The question of how long it would take to cross the Milky Way is, in the end, a question about our place in the cosmos, about how small we are and how vast the galaxy is, about what's possible and what's not, about the relationship between human ambition and physical reality. These are the facts. The physics is clear. The distances are measured. The time scales are calculated. But the deeper truth is simpler. We don't need to cross the Milky Way. We're already home, right here, right now. In this one extraordinary galaxy that gave us stars, planets, the building blocks of life, and a view of the cosmos that stretches from one edge of its disk to the other. But let's push this exploration even further, because there's another dimension to crossing the galaxy that we haven't fully addressed. The practical question of survival. You can calculate how long the journey takes. You can work out the physics of near light speed travel and time dilation. But can a spacecraft, can a crew, actually survive the journey? Space is not empty. This is a critical point that often gets overlooked. When we talk about the vacuum of space, we mean it's mostly empty, but mostly is not the same as completely. Between the stars, there are atoms, mostly hydrogen, some helium, traces of heavier elements. The density is incredibly low. In interstellar space, you might find 1 atom per cubic centimeter. On Earth, air at sea level contains about 10 quintillion molecules per cubic centimeter. So interstellar space is about 10 billion times less dense than air. It's as close to perfect vacuum as anything gets in nature. But when you're traveling at 99.99999%, the speed of light, even 1 atom per cubic centimeter becomes a problem. Because kinetic energy depends on velocity. Specifically, kinetic energy equals 1/2 times mass times velocity squared. At high speeds, that squared term makes a huge difference. An atom of hydrogen hitting your spacecraft at 99.9999% light speed carries enormous energy. Each impact releases energy comparable to a particle in a high-energy physics accelerator. Not one impact. Billions of impacts per second as you plow through the interstellar medium. The cumulative effect would be like flying through a continuous stream of radiation. Your spacecraft would heat up. The hull would erode. Without adequate shielding, the crew would receive lethal doses of radiation. This is not a small engineering problem. You'd need shields made of something that can absorb or deflect these high-energy impacts. Perhaps a thick layer of material at the front of the spacecraft. Or a magnetic field to deflect charged particles. Or a cloud of gas or plasma pushed ahead of the ship to absorb the impacts before they reach the hull. All of these solutions add mass, complexity, and energy requirements. They make the journey harder, not easier. And we haven't even talked about dust grains. Interstellar space contains tiny particles of dust, grains of carbon, silicon, various compounds. They're microscopic, typically less than a micrometer across. But at near light speed, a dust grain impacts with the energy of a bomb. A grain, 1 micrometer across, traveling at 99.9999% light speed, hits with energy equivalent to several kilograms of TNT, one dust grain. And interstellar space contains billions of them per cubic kilometer. On a journey across the galaxy, you'd encounter countless dust grains, each one a potential catastrophe if it breaches your shielding. Avoiding them is impossible. Space is too vast, the grains are too small and too numerous. You can't steer around them all. You have to go through them. That means your shields have to be good enough to handle continuous impacts from particles ranging from individual atoms to dust grains. And they have to do this for years of ship time, decades, or centuries of outside time. The engineering challenges are staggering. But let's assume they're solvable. Let's assume some future technology develops materials or field systems capable of protecting a spacecraft during high-speed interstellar travel. There's still another problem: acceleration and deceleration. To reach near light speed, you have to accelerate. And unless you plan to fly past your destination at full speed, you also have to decelerate. Both processes take time and energy. How much time depends on how much acceleration you can tolerate. Humans can handle about 3 or 4 times Earth's gravity for extended periods. Fighter pilots can briefly experience 8 or 9 times Earth's gravity with special suits. But sustained high acceleration is dangerous. It compresses your circulatory system, makes it hard for your heart to pump blood to your brain. It can cause blackouts or worse. Let's say we limit acceleration to 1 times Earth's gravity, or 1g. That's comfortable, equivalent to standing on Earth's surface. You could live at 1g indefinitely, without harm. At 1g acceleration, how long does it take to reach near light speed? The speed of light is about 980 million meters per second. Acceleration at 1g is 9.8 meters per second squared. Divide speed by acceleration and you get time, about 1 year. If you accelerate continuously at 1g for 1 year, you reach light speed. Except you can't actually reach light speed because of relativity, but you can get arbitrarily close. So let's say you accelerate at 1g for 1 year. You reach 99+% of light speed. Your ship is cruising. Now you coast for a while, covering vast distances. Eventually, you need to decelerate. Another year at 1g deceleration. Total time from your perspective, about 2 years of acceleration and deceleration, plus however long you spend cruising. That sounds manageable. But here's the problem. Accelerating at 1g for 1 year requires energy. A lot of energy. Let's calculate it. Suppose your spacecraft has a mass of 1,000 tons, or 1 million kilograms. That's small for a deep space vessel, but let's use it as a baseline. The kinetic energy at 99% light speed is roughly equal to the mass times the speed of light squared, times a relativistic factor. For 99% light speed, the kinetic energy is about 7 times the rest mass energy. Rest mass energy equals mass times speed of light squared. For 1 million kilograms, that's about 900 sextillion joules. Kinetic energy at 99% light speed is about 7 times that, roughly 6,000 sextillion joules. That's the energy you need to input to accelerate the spacecraft. Where does it come from? If you're using a rocket, you carry fuel, but fuel has mass. And you need energy to accelerate the fuel too. This creates the tyranny of the rocket equation. The more fuel you carry, the more mass you have, the more fuel you need to accelerate that mass. It spirals out of control very quickly. Chemical rockets can't do it. Nuclear rockets might get you a small fraction of the way. Matter-antimatter annihilation is the most efficient possible fuel, converting mass directly to energy. But even with perfect efficiency, the fuel requirements are staggering. You'd need to carry fuel with mass comparable to the spacecraft itself. And you'd need to carry fuel for deceleration too. Alternatively, you could use an external power source. A laser beam fired from the solar system could push a light sail attached to your spacecraft. As long as the laser keeps firing, you keep accelerating. No need to carry fuel. But lasers diverge with distance. A laser beam spreads out as it travels. To push a spacecraft to another star, you'd need a laser so powerful and so tightly focused that it boggles the mind. And it would only work for acceleration. For deceleration, you'd need a laser at your destination, which means either someone already there to operate it or some other method. The energy problem is fundamental. Accelerating to near light speed requires enormous energy input. There's no way around it. And that energy has to come from somewhere. Either you carry it with you, which adds mass, or you beam it from outside, which requires infrastructure on a scale we can barely imagine. Let's think about another approach. What if instead of one long journey, you make many short hops? You travel from Earth to the nearest star, about 4 light years. Then from there to the next nearest star, maybe another 4 or 5 light years. Hop from star to star across the galaxy. Each individual hop is shorter, but there are a lot of them. The Milky Way is about 100,000 light years across. If the average hop is 5 light years, you need 20,000 hops to cross the galaxy. At each hop, you decelerate, perhaps spend some time at the star system, then accelerate toward the next destination. If each hop takes, say, 10 years of ship time, including acceleration, deceleration, and exploration, 20,000 hops takes 200,000 years of ship time. That's back to generation ship territory. So hopping doesn't really save you time unless you're only exploring a small region, not crossing the entire galaxy. It's also worth thinking about navigation in more detail. Space is 3-dimensional. The galaxy is not a flat disk, it has thickness. The disk is about 1,000 light-years thick, with most stars concentrated in a thinner layer about 300 light-years thick. But there are stars above and below the plane. The halo extends much farther, thousands of light-years above and below the disk. When you're crossing the galaxy, you have to choose a path through this 3-dimensional structure. Do you stay in the plane, where stars are more densely packed? Do you rise above or below the plane to avoid crowded regions? Different choices have different implications. In the plane, you're more likely to encounter stars, planets, potentially interesting phenomena. But you're also more likely to encounter obstacles, regions of dense gas or dust, hazards. Above or below the plane, space is clearer, fewer obstacles, easier navigation, but also fewer landmarks, less to explore. The optimal path depends on your goals. And the path affects travel time because the shortest distance between 2 points is a straight line, but a straight line might take you through regions you want to avoid. A longer path that routes around hazards might actually be faster and safer. There's also the question, of course, corrections. Over a journey of 100,000 light-years, even tiny errors in navigation compound into huge deviations. If your initial heading is off by just 1 degree, after 100,000 light-years, you'd miss your destination by thousands of light-years. You'd need constant course corrections. That means slowing down, adjusting direction, speeding back up. Each correction costs energy and time. Or you use instruments to continuously monitor your position and make tiny adjustments to your trajectory. But instruments can fail. Calibration can drift. Over a journey lasting decades or centuries, equipment degrades. Redundancy becomes critical. You need backup systems for your backup systems. The spacecraft has to be designed for long-term reliability in ways that no current technology approaches. Consider also the human factor for a crewed mission, or the biological factor if we're thinking about preserving life rather than just machinery. Humans need food, water, air, waste, recycling. All of that has to function perfectly for the duration of the journey. A closed-loop life support system that can operate for years without resupply or maintenance. We've tested closed-loop systems on Earth. Biosphere 2 was an attempt to create a self-sustaining ecosystem in a sealed environment. It ran into problems. Oxygen levels dropped. Carbon dioxide built up. Food production was insufficient. The experiment showed how hard it is to create a stable, self-sustaining ecosystem, even when you have abundant solar energy and the resources of Earth nearby. In a spacecraft crossing the galaxy, you have to get it perfect. One failure, one broken link in the ecological chain, and the crew suffocates or starves. There's no possibility of resupply, no calling for help. You're on your own. This is why many proposals for interstellar travel focus on suspended animation or cryogenic freezing. If the crew can be put into a state of suspended metabolism, they don't need food, water, or air during the journey. You'd only need to keep them alive at minimal levels, frozen or in a deep sleep, then revive them at the destination. But we don't have that technology. We can freeze cells, embryos, even small organisms. But freezing a human and reviving them later without damage is far beyond current medical science. Ice crystals form during freezing and rupture cell membranes. You could use cryoprotectants, chemicals that prevent ice formation, but they're toxic at the concentrations needed to protect an entire human body. Some animals survive freezing naturally. Wood frogs freeze solid in winter and thaw out alive in spring. They produce glucose and other compounds that protect their cells from ice damage. If we understood that process fully, if we could replicate it in humans, cryogenic freezing might become possible. But we're not there yet. So for now, any crewed journey across the galaxy would need a fully functioning life support system and a crew awake and active for at least part of the journey. Or it would need to be a generation ship where multiple generations live and die during the voyage. And that brings up social and psychological challenges. How do you maintain a stable society on a generation ship? What's the governance structure? How do you resolve conflicts when there's no possibility of leaving or calling for outside help? How do you maintain morale and purpose when the journey is longer than any individual's lifespan? These are not trivial questions. History shows that isolated communities can develop in unexpected ways. Sometimes they thrive. Sometimes they collapse into conflict. On a generation ship, there's no backup plan. If the society fails, everyone dies. You'd need to carefully design the social structure, education system, cultural traditions, everything that holds a community together. And you'd need to ensure it can adapt and evolve over generations, while still maintaining enough stability to complete the mission. It's social engineering on a scale never attempted before. Now, let's talk about what you'd actually see if you made this journey. We've discussed the technical challenges, the physics, the energy requirements. But what about the experience? What would it be like to cross the Milky Way? First, the view. From inside the Milky Way, from our position in the galactic disk, we see the galaxy as a band of light across the sky. That's because we're looking through the disk edge on. In one direction, toward the galactic center, the band is brighter and denser. In the other direction, toward the outer edge, it's dimmer. As you move through the galaxy, this view changes. If you travel perpendicular to the disk, rising above or below the plane, the Milky Way band would gradually resolve into a disk shape. You'd see the spiral arms more clearly. The structure would become apparent. Instead of a band, you'd see a spiral, like looking down at a pinwheel. The view would be spectacular. A galaxy spread out before you, billions of stars in intricate patterns. But you'd also be leaving it behind. The farther you get from the disk, the more isolated you become. Fewer stars nearby, darker skies. Eventually, if you went far enough, you'd leave the Milky Way entirely and enter the darkness of intergalactic space. From there, the Milky Way would look like a small spiral seen from outside, beautiful but distant. If you're traveling within the disk, crossing from one edge to the other, the view changes more gradually. Stars drift past. Some grow brighter as you approach, then fade as you pass and move away. New stars appear ahead, dim at first, then brightening. Constellations dissolve and reform. Patterns that were familiar become unrecognizable. Near the galactic center, the sky would be crowded, so many stars that they blend together into a continuous glow. The night sky would never be truly dark. Farther out, toward the edge, stars become sparser, more darkness between the lights. A lonelier view, but still beautiful. Throughout the journey, you'd see nebulae, some small, some enormous, spanning tens or hundreds of light years. Glowing clouds of ionized gas in reds, greens, blues, the signature colors of hydrogen, oxygen, and other elements. Dark nebulae too, clouds of dust that block light, appearing as dark patches against the starry background. You'd see regions of active star formation, bright blue stars clustered together, still surrounded by the gas from which they formed. And regions of stellar death, supernova remnants, expanding shells of debris glowing from the energy of their explosions. Every few thousand light years. A different view, a different environment. The galaxy is not uniform. It's a patchwork of different regions, each with its own character, and you'd see all of it on a journey across its full width. There's also the question of time perception. We've talked about time dilation. From the traveler's perspective, if you're traveling fast enough, the journey might only last months or years. But from an outside perspective, centuries or millennia pass. This disconnect would create a strange experience. Looking out the window, watching stars drift past, each one representing years or decades of outside time. By the time you've passed a single star, generations have been born and died back on Earth. Empires have risen and fallen. The entire course of human history could play out in the time it takes you to cross a small section of the galaxy. It would be disorienting, isolating. You'd be moving through space, but also through time, watching the universe age around you while you remain relatively young. This is the price of high-speed travel. You can cross the galaxy in a survivable time frame from your own perspective, but you lose any connection to the time and place you came from. Now let's consider what happens when you arrive. Suppose you successfully cross the Milky Way. You've traveled 100,000 light years. You reach the far edge of the galactic disk. What now? If you're an automated probe, you might begin observations. Study the local stars and planets. Send data back to Earth, knowing it will take 100,000 years to arrive. If you're a crewed mission, you might search for a habitable planet, somewhere to land, to rest, perhaps to settle. But 100,000 years have passed back home. Even if you send a message announcing your success, it won't reach Earth for another 100,000 years. 200,000 years, round trip. Everyone who sent you is gone. Their civilization might be gone. Humanity itself might have changed beyond recognition or might not exist at all. You're effectively alone, cut off from your origin. This is the fundamental reality of crossing the galaxy. Even if you succeed, even if you survive the journey and arrive safely, you can never really go home. Home doesn't exist anymore. Too much time has passed. You're a relic from the ancient past, preserved by the physics of high-speed travel. Your only option is to move forward. Explore your new surroundings. Build a new home if you're a crewed mission. Or continue onward if you're a probe, perhaps leaving the Milky Way entirely and heading toward another galaxy. But the Milky Way is small compared to intergalactic distances. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. At light speed, that's 2.5 million years. Even the Magellanic Clouds, small satellite galaxies orbiting the Milky Way, are about 160,000 light-years away. Crossing to another galaxy would be a journey of an entirely different magnitude. The Milky Way is our cosmic neighborhood. Crossing it is hard enough. Crossing to another galaxy is exponentially harder. So, in a sense, crossing the Milky Way represents the limit of what might be achievable. Beyond that, the distances become truly insurmountable unless new physics emerges, unless we discover something fundamental about the universe that we don't currently understand. Wormholes, warp drives, hyperspace, or something else entirely. But based on what we know now, the Milky Way is the arena in which any future human or post-human civilization will operate. It's our home. And if we ever spread beyond Earth, if we ever explore other star systems, the Milky Way will be our boundary. 100,000 light-years. That's the scale of our cosmic home. Vast enough to contain hundreds of billions of stars. Vast enough to take light 100,000 years to cross. Vast enough to dwarf human comprehension. And yet, small enough to comprehend intellectually. Small enough to map, to study, to understand. We know its size, its shape, its structure. We know how it formed and how it will evolve. We know where we are within it. We've measured the distances to thousands of stars, mapped the positions of millions more. We've observed the galactic center, the spiral arms, the halo. We've detected planets around other stars and found that they're common. We've listened for signals from other civilizations and found nothing so far. But we keep listening. The Milky Way is ours to study, perhaps one day to explore. But crossing it, truly traversing its full width, remains one of the greatest challenges imaginable. Not impossible. The physics allows it. But difficult, beyond current capability. Maybe that's how it should be. Maybe the Milky Way's vast size serves a purpose. It ensures that any civilization that arises within it has room to grow, to expand, to explore, without immediately bumping into neighbors. It creates isolation, yes, but isolation also creates diversity. If there are other civilizations in the Milky Way, they're separated by distances so great that each develops independently. Each follows its own path. Each creates its own unique culture, technology, philosophy. When we finally do cross those distances, if we ever do, we'll encounter something truly different. Not just another civilization, but an entirely independent, evolutionary, and cultural lineage. That's worth preserving. That's worth the isolation. The Milky Way's size creates the possibility of diversity on a cosmic scale. And that diversity, that variety of independent paths through the space of possibilities, is valuable, perhaps irreplaceable. So, when we ask how long it would take to cross the Milky Way, we're asking about more than just travel time. We're asking about the nature of our cosmic home, about the distances that separate us from other stars, other possible worlds, other possible civilizations, about the isolation imposed by the galaxy's vast scale, and about what it would take to overcome that isolation. The answer is complex. Physically, 100,000 years at light speed, practically, perhaps achievable in a survivable time frame with near light speed travel and time dilation, but always at the cost of disconnection from home, always requiring technologies we don't yet have, always pushing the limits of what's possible. The Milky Way is vast. Crossing it is one of the ultimate challenges. Not impossible, but difficult enough that it will require everything we have. All our science, all our engineering, all our determination. And even if we succeed, even if we cross those 100,000 light years, we'll arrive as strangers in a strange land, separated by time as well as space from everything we knew. That's the reality. That's what it would take to cross our galaxy. But the deeper question is not can we, but should we? And that's a question each generation will have to answer for itself, right here, right now. In this one extraordinary galaxy that gave us stars, planets, the building blocks of life, and a view of the cosmos that stretches from one edge of its disk to the other. The journey across the Milky Way isn't measured in years or light years. It's measured in understanding. And that journey, the one that matters most, we've already begun. Thank you for joining me on this exploration tonight. If you found value in this journey across space and time, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the cosmos. And remember, the next time you look up and see that band of stars stretching across the night sky, you're looking at home, a structure so vast that light takes 100,000 years to cross it. So vast that we'll likely never traverse it physically, but so familiar that we've mapped it, understood it, and made it part of who we are. The Milky Way is immense. We are small, but we're here. We're part of it, and we understand it. And that's extraordinary. Good night, and sleep well under the stars of our vast, beautiful, forever home.